Okay, thank you. Yeah. So our group received research support from GE Healthcare. So many non-Cartesian imaging trajectories have this property that they sample densely in low-frequency regions and sparsely in high-frequency regions. And so this variable density sampling property has a number of benefits. One is that it enables auto-calibration parallel imaging methods. It is also in general more robust to motion because we have some averaging in the low-frequency regions. On the other hand, it is also a challenge for iterative reconstruction. On the right, I'm showing a 2D UT compressed sensing reconstruction. And you can see that even after 30 iterations, there is still significant blurring in there, showing that it has not converged. And so the overall goal of this work is to accelerate iterative reconstruction convergence for these types of acquisitions so that it will be more clinical suitable for applications. So to put things more concretely, we're going to consider the following objective functions. We have the data consistency term with image X, the non-Cartesian sense operator A, and then the k-space signal represented by Y. We also have regularization term that can either be L1 wavelet or total variation, depending on your applications. And for iterative reconstruction, we often perform the following step, where we perform a gradient step of the gradient consistency, followed by the proximal operator of the regularization. And if we do this many, many times, eventually we'll converge to an optimal solution. But the problem is, how fast can we converge to a good enough solution? And that's actually determined by the condition number of the A adjoint A operator. The higher the condition number is, the slower the convergence. And for variable density sampling, the condition number is in general quite high, and so we get slow convergence. And so a practical heuristic to deal with this issue is using density compensation. And it leverages efforts in gradient reconstruction. And operational-wise, we put the density compensation in k-space, and in each iteration perform it. This is very simple to do and very fast, and empirically has been shown to accelerate convergence. But one of the major issue here, and noted by many works, is that if you go back and see what you're changing in your objective function, you're basically throwing away samples for convergence. So you're throwing away low-frequency regions for convergence, which is in general something that we don't want to do. And so a more correct way to accelerate these types of algorithms without the SNR penalty is through preconditioning. And operational-wise, instead of putting the weights in k-space, we actually perform a precondition operations after the A adjoint A operation. And together, we would get an improved condition number. And so both theoretically and empirically, it has been shown by many work that this would accelerate convergence. Now, this is still not perfect. It still has some issue. One is that now the preconditioner is applied in image domain. And so to compensate variable density, in k-space, you have to do additional Fourier transforms. In addition, incorporating preconditioners in regularization, the proximal operator, it's non-trivial. Often you need using ADMM or other methods that require inner loops. And all these together means that you overall would increase the computational complexity. And so even though we've reduced the number of iterations, each iteration actually costs more now. And so together, it makes sense that we should combine the benefits, the advantages of each method, right? Like ideally, we should have the computational efficiency of density compensation and the SNR of preconditioning. And recently, there's a work from Tredesco that showed that indeed you can actually do preconditioning in k-space, but there's still some drawback of having inner loops and using off-the-shelf density compensation factors. And so our contribution is to generalize this work and present a more general case-based preconditioning method that does not have inner loops using the primordial hybrid gradient method. We then go on and derive an explicit L2 optimized case-based diagonal preconditioner to accelerate convergence. And we demonstrate in experiments that we can get convergence for 2D acquisitions in about 10 iterations. So how can we precondition in K-space? So if you look at our objective function, this is convex and then constrained. And so these types of problems always have a dual problem. And the dual problem is closely connected to a primal end. So if you solve one, you can bring it back to the other one. And if you stare at the dual problem close enough, you find that the dual variable actually lives in K-space. And so the key observation here is that we can solve for the dual problem and precondition it in K-space with a density compensation-like operation and then get back the image. And one method that we use is the primal dual hybrid gradient method, which solves the primal and dual problems together. And these two are the update steps that we're going to use. But the key takeaway here is that per iteration, the computational complexity is the same as the vanilla iterative reconstruction that I showed. In addition, now we can basically precondition the dual variable in K-space to accelerate convergence. So now that we know how to precondition in K-space, we can then go on and optimize and design a preconditioner for it. And here we chose the L2 norm as an optimization criterion. It's not the only one that we can choose, but we chose it because of simplicity and also computation efficiency. Because of time, I won't be able to go into the detail, but I'll point out one interesting feature, is that the preconditioner actually incorporates sensitivity maps into it. And so compared to density compensation, an interesting feature is that each channel actually has a different preconditioner. And so on the bottom, I'm showing a preconditioner of a 2D variable density spiral trajectory with 8-channel sensitivity maps. And so along the readout, each line, each curve right here is a preconditioner for each channel, and you can see they're different. Overall, you can see that it does what you expect, where in low frequency, it weighs it down because it's more dense, and in high frequency, it weighs it up because it's less dense. But each channel is different, and so it provides more degrees of freedom. And an intuitive explanation is that in sensitivity maps, we also have some linear phase in it. And so in K-space, what this means is that you have some shifts. And so when you want to compensate density for multi-channel, you should really take into account these linear phase together for multi-channel systems. So now that we have the algorithm and also the preconditioner, we applied to data sets and compared with existing methods. And so on the left and middle, there are existing methods. And just going through the iterations, you can see that the proposed method converges pretty fast. In particular, if we stop at iteration 5, you can see the existing methods comparison have some blurring, whereas the proposed method has essentially converged. Here's another more extreme examples where we apply it to 2D UT radio. Because of RAM sampling, it has more variable density in K-space. Going through the iteration, you can see the proposed method has basically converged. Even after 30 iterations, the other two methods haven't converged. Pausing at iteration 10, you can see that there's a huge difference in image quality. So in conclusion, we've shown a method that allows us to accelerate iterative reconstruction convergence without the SNR penalty of density compensation or the increased computations of existing preconditioners. We've explicitly derived an L2 optimized K-space diagonal preconditioner, and one interesting feature is that it's different for each channel. And we've shown in experiments that we can achieve convergence in about 10 iterations. And thank you.